up and down, they get tripped, they get full, till now they become turbulent. So the roughness on the ball will allow us to promote the boundary layer to become turbulent. So way back in the early days, they simply used some sand to induce transition. In that, even though the boundary layer, or rather, even though the Reynolds number is not 5 million, by tripping it or fooling the boundary layer using roughness, we can make the boundary layer to behave like a turbulent boundary layer. So we fool the boundary layer to behave like turbulent, even though I'm still within the 5 million Reynolds number range. And hence the reason for the dimples on the golf ball. And many different manufacturers will title this. Callaway will claim they do a lot of research in the laboratory to change the shape of those dimples from maybe a quarter of a circle to a teardrop, claiming that my golf ball will fly further than yours for the same launch speed. Yes?
Does that actually change the Reynolds number?
No, it doesn't. Reynolds number is only dictated by the parameter that we mentioned, which for the case of the golf ball, only the velocity. So the Reynolds number stays the same. By putting roughness on the surface, the boundary layer will fool or trip or think that I'm now behaving like turbulence. Instead of layers, I'm now dancing up and down because of all those roughness. And I have a lot of more random energy. And I behave more like a turbulent boundary layer that can fight against that adverse pressure gradient longer. If I'm laminar, I get so tired, 80 degrees, I say bye-bye, and I get separated. But with that added momentum, just that tiny bit, I can continue on for another 120 degrees. At the point where which I finally get so tired, I peel off. But the difference between that form drag and this form drag is a factor of 2. Whereas the skin friction drag obviously still come into play, but for blunt object, not an airfoil, very often is the pressure drag or the form drag that is dominating, not the shear. Yes?
How does this affect how straight the ball flies in the case of this ball?
It doesn't. It's a different that is spin. That is totally unrelated to what we discussed here. That's a different phenomenon. Just like a baseball, how do you make it toss a drop ball, a spin ball, and all that are totally unrelated to this phenomenon. Yes? The quick answer to that is you try to put the motion of the ball where you create a pressure field around the ball to affect the trajectory. So a straight ball versus a fast ball versus a spinning ball, all because of the motion of the ball creating a pressure field that changes the trajectory. I mean, if you play volleyball, you serve the volleyball, a floater is a ball where it's so stationary, as it comes to you, the ball is floating. And that's because the pressure field with the ball is not spinning, the pressure field is so unstable. The ball is actually, like it's as though it's floating. All right? So that is totally unrelated to this. Totally unrelated. Yes?
Does this apply to shapes that aren't spherical?
Yes. So the question is, what if I have an airfoil? Right? What my airfoil that if I want to be, when on the airfoil you always have, again, any plate or airfoil always a region where the foil is first laminar and then you go into turbulent. And the ability to trip and fool that boundary layer to become turbulent can be deployed to negotiate against that pressure gradient. But this other trade-off on the airfoil, it turns out the friction drag is much more dominating than that for a blunt object. So you now have to consider them as a trade. If that makes sense to you. Yeah, so it's a compromise. You try to design a shape that will optimize both or reduce both the form drag and the skin friction drag. All right, I mean, what I'm trying to say is, yes, there is technique you can try to deploy. Some typical airfoils like this, and the weight is kind of like that. I can, on the basis of what we talk about, to reduce the form drag, I can design an airfoil that's much, much longer, so the weight is a fraction of what it is before. But what happened here is you're increasing the friction drag, right? So you need to compromise that. No different than a blunt object. Yes?
Similarly, for the shape, the hull of a boat is skin friction drag.
Say again?
Similarly, for like the whole shape of a boat is skin
Yep.
friction drag consequential as well as like
Both,
well,
on a boat, you have both skin friction drag. Only the wetter surface is important then, right? So on a boat, you have the skin friction drag, but the weight created by the boat, the lower pressure behind the boat, also create drag. And that's why you streamline it. Right? Remember I talked about the shape of a fish being like this? It's nature in millions of years, for all the evolution, make the fish to be very streamlined. So both the shear stress when they cut through water and the form drag is minimum. So it can swim very efficiently in water. And that's why you never see a fish like this. It won't survive. Right? Some of them do. But that's the reason. Right? So most cases, both friction drag and form drag come into play. And we as aerodynamicists being paid to make those devices more efficient is find out a shape or other trait, like tripping the boundary there, to make the drag go smaller. That's what you get paid for to do. So 1% difference in the efficiency of that airplane up there is millions of dollars of fuel burn per engine per year. And that's what you're trying to do. Okay? Other questions? Okay, so we take a short break, and when we come back, I can do a little bit on the test problem